Okay, the next talk on tensor PCA, and Yuan will give the talk.
Okay, first I apologize for my voice. So this is based on the journal with Nima Nakuma, Runger, and Jose Mobahi. So to start with this talk, let's first talk about the basic difficulty we are facing when we are solving a convex optimization problem. So in a convex optimization problem, we try to optimize the smooth function. If we try to apply the local search method, however, the local search method may get stuck in a local optimum. So we cannot hope that we can converge to a global optimum all the time. So how can we get rid of this local optimum? So one possible solution that we can think about is that perhaps we can smooth function. And in this talk, I will particularly consider Gaussian smoothing. So the Gaussian smoothing means that we try to convolve the function with a Gaussian function with mean 0 and variance t. So here t controls the smoothing level. So when t is 0, we basically get the original function. So if we choose this t properly, then maybe we can get rid of the bad local optimum. And the function is well behaved. But however, we should also notice that the global optimum somehow shift. So here we have two problems. One is that how to decide how much to smooth so that we can get a well-behaved function. Another question is how to recover the original global optimum, since now the global optimum is shift. So here comes the homotopy method. A homotopy method must stress that we should try all levels of smoothing. So basically, homotopy method we start with a sufficiently large amount of smoothing. So for example, in this case, t equals to 3, so that we can get a well-behaved function, have a unique local minimizer. And then we gradually decrease the smoothing level, and then follow the local optimum. So basically, it means that when we decrease the smoothing level from t equals to 3 and t equals to 2, then we use the local optimum we recover for t equals 3 as the initial solution, and then we apply the local search method again. So repeat this procedure until t equals 0. Then we get back to the original solution. So basically, the homotopy method is guaranteed to converge to a local optimum. However, can we show that you will converge to the global optimum too? And actually, homotopy method has applied to multiple areas of application. However, there are no theoretic guarantee on the quality of solution. And recently, there are two seminal works try to establish such theoretic guarantee on the global convergence. However, either the assumption is too restrictive or the condition is too difficult to check. Another problem of the homotopy method is that we somehow need to handcraft the choice of smoothing level. So we need to decide what level of smoothing we are going to choose in these intermediate steps. And also, in general, the homotopy method may be slow because we need to apply the local search method repeatedly for each level of smoothing. And in this work, we particularly apply the homotopy method on a specific problem, tensor PCA problem, which was first introduced by Richard and Montanelli in 2014. So let's recall what is the standard matrix PCA problem. So basically, we try to recover a unique vector V in dimension D, such that, and with a signal-to-noise ratio tau, and we try to recover this signal in a noise matrix. So the noise matrix is expressed by tau times the outer product of V plus Gaussian noise matrix. And in the tensor PCA, we simply replace the outer product of V by a third tensor of V. And actually, you can view this outer product of V as the second order of tensor of V. And our objective is that we try to design efficient algorithm for as small tau as possible. And about principles, so in the seminal work, they show that they can recover V when tau is in the order of omega d. Actually, they show that the algorithm can work by a simple local search method. Okay, and if we have exponential time, they show that we can recover the signal with a signal-to-noise ratio in the order omega square root of d. And in 2015, Hopkins, Shi, and Stewart, by using a sum of squares technique, they can recover V when tau is in the order d to the 3/4 in poly time. The basic sum of square algorithm is somehow slow, and the learning time is improved to nearly linear. And in our work, basically, our algorithm is somehow inspired by the homotopy method, but in the end, we will somehow shows you that by a slight modification of the local search method, we can get this guarantee in point in time. So basically, our result is that we match the best known result on the guarantees, and we can use less extra space. And actually, we have a better convergence rate when tau is extremely close to the lower bound of the guarantee. And this is one of the first results, as we know, on provably analyzing homotopy method. So let's give you some intuition about the algorithm. So first, in order to solve the tensor PCA problem, we model this problem as an optimization problem. So we call that for the matrix PCA problem. What we do is that we try to find a unique vector X so that we maximize this quadratic form X transpose MX. And in the tensor PCA, similarly, we optimize this cubic polynomial. And here we replace the square of the inner product between V and X by a cube of the inner product of V and X. And here I give you some intuition about the shape of the function. So it indeed has a lot of spurious local minimum around the equator, but while the function looks well when it has a good correlation with V. So from homotopy method, so basically the first step is that we need to analyze what is going on if we have infinite smoothing. And actually, infinite smoothing gives us a unique optimum, and it has a non-trivial correlation with the signal V, with d to the minus 1/4. And actually, if we compare it to a random univector, which can only give you d to the minus half. So basically, at the very beginning, homotopy method actually gives us some useful information. And in this work, the main lemma we show is that as we call the phase transition in the homotopy method. So basically, it says that there is a threshold theta such that when the smoothing level is larger than theta, the function is somehow well behaved. And when the t is less than theta, the function looks like the original function. And in particular, we show that if we use infinite step of the smoothing in the homotopy method, so basically we use d continuously from t equals to infinite to t equals to 0, then what we can show is that the local maximizer you got when t larger than theta is close to S star. Here S star is the unique optimizer we get when t is infinite. And when t is less than theta, then we show that the maximizer we get is actually has omega 1 correlation of the signal V. So based on this lemma, we can significantly simplify the homotopy method. So here, basically, for the first phase, we only need to choose one point. That is t1 equals to infinite. And for t less than theta, the second phase, we only need the original function, t2 equals to 0. Then that would be our algorithm. So basically, we use the infinite smoothing to compute S star as the smart initialization point. And then we will reduce our smoothing level directly to 0 and apply the power method at 0 smoothing. So as a conclusion, we show that homotopy method can give nearly optimal results for the tensor PCA problem. And we also show that it's possible to analyze non-coercive function even when they really have bad local optimum. So currently, people try to escape this local optimum by showing that either we don't have this bad local optimum or all bad local optimum is indeed good enough in the sense that the solution is close to the global optimum. So I will stop here. Thank you.
Questions? Okay, I have a question. Is there a method? Can your method extend to tensor PCA problems with noise different from Gaussian?
We are not sure about that. Yeah, we haven't tried to analyze the noise other than Gaussian. But I believe that since the shape of the optimization, the shape of the function looks the same, so maybe we can try to apply the similar smoothing method, but we use a different kind of distribution that would match the noise we have, and then we can get a similar guarantee.
Okay, let's thank the speaker again.
you.